So for this particular problem, it's just a number of similar springs, each having the same spring constant, are joined in 4 arrangements as shown below. It says the same load is applied to each arrangement. Which arrangement gives the greatest extension? Okay, so in this diagram here, you have 2 springs in parallel, and here you have a combination of springs. Here you have 2 parallels that's hooked up, and then that's hooked up in series to another 2 parallel. And then in diagram 3, you have 2 parallels, which is hooked up to a single another spring in series. And then the Roman numeral 4 is 3 springs in parallel, which is hooked up to another spring in series. All right, and each of these will have the same load as stated in the problem. So it says each of these have the same spring constant, so I'm just going to call it K. So I'm going to give each of these springs a K. So as you practice, make sure you read problems correctly. I'm calling all of these K's because they said so, okay? Well, in order to figure this problem out, you have to know Hooke's law. Hooke's law is F is equal to Kx. But the question here asks for the greatest extension, so I isolate for x simply by dividing both sides by the k in the function. But you notice here it says F load. Why? Because each of these arrangement has the same load, which is just the weight of the system. Here I'm just gonna call it F load. You can call it W for weight if you want. In the denominator here I call it K effective total. I have to figure out what the total spring constant is for each of these diagrams. So I'm just going to call that K effective, and it has to be total because I'm combining all the springs into just one. All right. So it wants us to find the greatest extension based on this function here, because they all have the same numerator, because the load is the same for each of these diagrams. The only thing that you have to really compare is the K effective. Well, how do you get the biggest extension? Well, in math, when you divide by a smaller denominator, you get the bigger value, okay? So we want to be able to figure out which one has the smallest K effective, because when you take the same numerator and you divide by the smallest number, you'll get the biggest answer. All right, so I want to keep that in mind. So here I made a statement for you. You want the smallest K total, because dividing by a small number gives you a bigger answer, which is what we want because it wants the greatest extension. All right, so let's go ahead and knock out Roman numeral 1. Here I see 2 springs in parallel, so I'm going to combine those 2 into just one spring. So the K effective, if I were to replace those 2 springs with just one spring, it would be 2K, because the function for 2 parallel springs is just K plus K. All right, so K plus K is just 2K, so the K effective for the first system is 2K. Let's go ahead and move on to number 2 here. Here again, you have 2 parallel springs, and that is hooked up in series with another 2 parallel springs. So I'm just going to combine. Watch what I'm doing. Here, those 2, I'm going to combine those 2 in parallel. I'm going to combine these 2 in parallel, and then those will reduce down to just this. Okay, so now I have 2 springs in series, but you have to combine these 2 top springs in parallel, and you have to compare these 2 bottom springs in parallel. So to do that correctly, the function for parallel springs is just K plus K. Here is K plus K because each of these springs is just K and K. So here I'm going to call it K effective 1. So I'm combining these first 2 springs properly. So K effective 1 is K plus K, which reduces down to just 2K. Okay. So that takes care of the top 2 springs in parallel. Well, I need to do the bottom 2 springs in parallel as well. So I'm going to call this K effective 2, just to differentiate between the combinations here. All right, so, well, these 2 springs are also in parallel, so it would just be another K plus K. So therefore, K effective 2 is simply also 2K. So now that I know these 2 values here, I combine 2 springs into one. And then now I combine 2 springs into another one. Now I can combine both of these springs in series to get one overall answer, okay? So what I'm about to do is combine these 2 springs here because they're hooked up in series. I need to make sure I use the proper function for it. So the K effective for a series is 1 over K plus another 1 over K, whatever K is, to the negative 1. Here, my denominator is going to be K effective 1 because that's my first spring. And then the second spring is K effective 2. And so I'm just going to go ahead and plug and chug. The numerator stays the same because that's just a 1. K effective 1 is replaced with 2K because that's what I found it to be when I combined them in parallel. And then K effective 2, similarly, is also 2K for this particular diagram. So the denominator for K effective 2 is also replaced with 2K. Well, this to the negative 1. So you got to make sure you add the stuff inside the parentheses first and then flip it. Okay. So here I have common denominators, 2K and 2K. So 1 plus 1 is just 2. And then 2K in the denominator stays the same because it sits over a common denominator. So 1 plus 1 is 2 right there. 2k is my common denominator. And then to get this particular function without the negative 1, you would just simply flip the quantity inside the parentheses. So it's now 2k over 2. Well, but 2k over 2 is just simply k because the 2 on top and 2 on the bottom cancel. So this is the k effective for the second diagram. Okay. All right, let's move on to the third one. Here I have a system as well, a combination system. I have two parallels, and those two parallels is hook up to the single one in series. So similarly, I can reduce this down to just two springs. I want to combine the top two springs in parallel, and then those two springs is now in series with the bottom one here. So here I have k effective 1 for the third diagram. Well, k effective 1, similarly to the one we just did in Roman numeral 2, it's just k plus k because these two are in parallel. When they're in parallel, you simply just add up the k constants. All right, so k plus k is 2k. So that's k effective 1 for the third diagram. And then the bottom one, I'm just going to call it k because, well, it's by itself. So it's just k. Now that we have k effective 1 and then k, we can just simply reduce the system down to just one spring. Again, these two are hooked up in series, so we would just similarly use the same process that we did for Roman numeral 2. So here, to add them in series, the k effective total now would simply be 1 over k effective 1, which is this spring right here. Then I'm going back and forth, and then now we got to account for the bottom spring here, which is just k. So that would just sit 1 over k. Well, now I'm just going to replace k effective 1 with 2k because that's what I found it to be. So here, I'm just going to do a quick substitution. It'll be 1 over 2k. And then this is just 1 over k, which hasn't changed. Well, 2k and k are not common denominators, so you have to find common denominator. You usually have to multiply the right fraction here by a 2 because this is 2k. So to have the same common denominator, you multiply this by 2, but you also have to multiply the numerator by 2, so it looks like this. So it'll be 1 over 2k plus 2 over 2k. Once again, when you multiply the denominator by 2, you always have to multiply the numerator by 2. Well, now that you have common denominators, you can do 1 plus 2, which is 3, and then it sits over a common denominator, which is just 2k. All right, so the parentheses just by itself reduces down to 3 over 2k, but now we got to flip it to get rid of this negative 1. So really, k effective total is just 2k over 3. All right, so that is our k effective for the third spring system. Now let's go ahead and let's do the fourth one. Here, you have 3 springs in parallel, which is hooked up to a series spring by itself. So I'm going to combine this top one just like the other ones. These are in parallel, so that's pretty easy to do. It's just k plus k, which is just 3k. Okay, so the one in parallel is super easy to do, but these two are now hooked up to this one in series. So I'm just going to do series. So it'll be 1 over 3k. All right, so here's this one, and that's 3k. So I'm just going to treat this as one spring. Well, what is the equivalent spring constant there? It would just be 3k. So it'd be 1 over 3k, and then this one is just k. So it'd be 1 over k to the negative 1. And then here we, like similarly to number 3, we have to find common denominator. This is 3k and that's k. So to get this right fraction to have the same common denominator, multiply it by 3, top and bottom. So now we have 3k as our common denominator. 1 plus 3 is simply 4, and then the denominator is just 3k. All right, so that's that pretty much. We're almost done here. So this is 4 over 3k, but we got to flip it, all right, to get rid of the inverse sign. So flip the 3k to the top, move the 4 to the bottom. So here we have 3k over 4. Well, if you look at everything I highlighted, so here we have 2k, here we have k, here we have 2/3 k, and here we have 3/4 k. Well, 3/4 is 0.75. 2/3 is 0.66, and 0.66 is less than 0.75, which is less than 1, which is less than 2. And as I stated earlier, you want the smallest k because it wants the greatest extension. So therefore, the answer for this one is Roman numeral 3 because it has the smallest k value. All right, I hope that helps. Stay nerdy, don't be wired.